Hello, everyone. Today we have Michael with us. Thank you, Michael, for accepting to give a talk at KUIS AI. I'm going to introduce you first. Actually, we met with Michael at the beginning of our PhDs in Sicily first, then at the conferences. He did his PhD with Professor Luc van Gaal at ETH Zurich, and then he started working as the head of AI at GIFs.com or GIFs.com. Michael, maybe you can enlighten us about this.
It's an open debate. It's an open debate.
I see. Okay, I'm going to say GIFs.com because GIF feels weird for some reason.
I agree.
And currently he is a research scientist at Google Research Zurich, working with Vittorio Ferrari. And today he's going to talk about his ongoing work there, I guess, adaptive and reusable networks, right? That's how you call it.
Yes, sorry, I didn't realize I didn't have my camera on, but now it's a good time to start that. Yeah, thanks, Fatma. Thanks a lot for introducing me. Exactly, I'll talk about some of my recent work in our group on reusable and adaptive models for visual recognition. And as Fatma said, I'm currently at Google as a research scientist. And so this is also kind of covered already. I did the PhD with Luc. Yes, so this is kind of repetition. If you want to get in touch with me, you find my Twitter handle here. But Fatma already covered that part. So let's talk about the contents of this presentation.
Michael, first, we don't see the slides at the moment.
I see. Wait.
Yeah.
Sorry, that is.
We see you though, but I mean, we saw you.
Aha, it's replacement. I thought I could see both. Okay. How do I? Then it was not a good idea to switch on my. Aha, I can only do either or, I guess.
I guess. Yeah.
So now you see my slides.
Exactly.
Okay. Okay, good. Then let's do it like this. Yeah, so I'll talk mostly about reusable and adaptive models, where I worked on 2 papers. The first one is towards reusable network components by learning compatible representation, which I'll actually present 2 days from now at AAAI, which is happening this week. And then I'll also present our paper on continuous adaptation for interactive segmentation by learning from corrections, which was presented at ECCV last year. I'll also briefly talk about our efforts in vision and language in our team, where I did some work on annotating with speaking and pointing. And then that was later continued by Jordi, actually, and turned into something very exciting, namely localized narratives. Let's see, somehow. Okay, I had some slide problems. Okay, so yeah, the first paper is towards reusable network components by learning compatible representations, which I did together with Jasper and Vittorio from our team. So currently, when you typically train models, you do so in silos with limited sharing. So what that means is you kind of want to solve a task, and then you train a model that solves your task, and you're happy, but you don't like share that model widely. And so typically, you know, if you train a model for segmentation, nobody else takes that and does detection with it or continues. And so there's no like sharing and reuse of knowledge that is kind of encoded through these trained networks. And typically it's kind of thrown away. So there's, except maybe that you often pre-train on ImageNet, that is kind of the exception, but there's limited sharing. And we want to kind of improve upon that. So our goal is to enable the reuse of model components. So this is kind of, the idea is that when you train models, well, often you have a feature extractor of some sort, and you have some task head, maybe a classification head or a segmentation head. And every time you train a model, you could add that to kind of a pool of models or a pool of components. And then our goal is that when you have a new task, you can quickly do well on that task by reassembling suitable model components. And the basic version of this is that you kind of take the right source model and fine-tune it. But here we want to go beyond just selecting full models, and we want to kind of, go a bit on the finer level and select components and reassemble them into a functioning model. And there's two main challenges to this. The first one is, how would you select components? Which components you expect to work well on your target task? And the second one is, how can you reassemble components into a well-working model? And here we focus on the second part. How can you make model components that you can reassemble? So more specifically, we want compatibility across network components. So the idea is that we kind of train two networks in the basic setting, and where we have some ping clouds that is a kind of a compatibility force that that tries to make the components compatible. So that if that works at test time, we can kind of swap their heads and build a kind of a Franken-type model, a new model that wasn't seen during training, but because the different components are compatible, or if they are compatible, such a model would still perform reasonable, and it would make non-random predictions. And here, again, we define components by splitting a normal neural network into what we call a feature extractor and a classification head. And we modify the training such that the components are kind of encouraged to become compatible. There's some related work on this. Often, or a lot of works, a whole line of work actually trains networks independently and then tries to understand whether these networks still kind of learn the same things. Did they learn the same features just in different order, or are at least some features similar? To what extent are they similar, or things like that? And the way they do it is typically by kind of taking the feature extractor of one model and the head of another, and then learning a stitching layer that maps the feature representation of one network to the feature representation of another network, so that then they're kind of in a space that is aligned. And then you can measure things like correlation or directly task accuracy. And in fact, the work by Lenk and Vedaldi, they do measure task accuracy after this stitching operation. So this is kind of similar to what we do, but they need to learn that stitching layer, and they do so by directly minimizing the task loss, say like cross-entropy loss. And so we want to not having to put a stitching layer that is then optimized in this new combination, but we want to modify the training procedure that the components are directly compatible, and we can just like combine them together into a new model that was not seen during training, and this new model would then directly perform well on some task. There's a bunch of other related areas. For example, in distillation, you typically train a large model or with a large feature extractor, and then you distill that information into a smaller feature extractor. So this is kind of compressing the information that you have in the large model into the small model. And here the model is essentially trained to copy the mapping of the large model. Multitask learning is also related. And I think maybe more relevant is continual learning, where in continual learning, a model is trained to solve some initial task, and then new tasks arrive in sequence and have to be solved. And to do that, often the model is then, or the feature extractor is then updated and optimized to work well on that next task, on the following tasks. But it should still work. The updated feature extractor should still work with the old task heads. So often this is done through some sort of regularization or some objective that prevents basically this updated feature extractor to change in arbitrary ways, so that it doesn't become incompatible, or in continual learning literature, this is often called catastrophic forgetting. So to prevent catastrophic forgetting. Now, we have several compatibility methods, which I'll introduce now. The first one is compatibility through rotation prediction. And here, the idea is that rather than independently training two networks we link them by having them solve some auxiliary task. In this case, we have a self-supervised rotation prediction task. So rather than just having a network, let's say that's trained on Cypher to classify into 10 objects like birds and ship and so on, we would also provide a randomly rotated version of the image to the network. And then the auxiliary task would be to classify what's the rotation of the image. And this is done here by this block visualized in blue here. And we have both networks, apart from their normal task, like classifying image into Cypher classes. We would also have them predict the rotation of the image. And in particular, we do this by having them both use the same auxiliary task head, so that basically their features, both of the features produced by the two networks, feature representations, they need to work with this shared head. And the idea is that then through this process, this kind of puts a constraint on the feature space that they can learn, and they need to both be compatible with this head. And then our hope is that they would be compatible more general, so that we could also take this head and put it onto the other network's feature extractor, and still that combination would kind of work because the features have a certain order and have a certain meaning, similar meaning in both cases. So this method is very general. The only requirement is really that we can, well, we use rotation prediction here, but you could just use any self-supervised task. And the only requirement is that you can define some meaningful self-supervised task for the data that you train your networks with. A variant of this is compatibility through discriminating common classes. So this is kind of the same idea, but if we train two networks on two datasets, and the two datasets are maybe both classification and have some classes shared between them, then this auxiliary task head here, again in blue, can just classify what class it is if the image has a class that is common between the two networks. But of course, this only works if indeed there's class overlap between the two tasks. The third variant is a very simple idea, is that if the two networks have identical architectures, we can just initialize them with the same weights. These weights can be random, or they can be produced by some sort of pre-training. And what this leads to is that initially, before we actually do any gradient descent, the networks are perfectly compatible because they're identical. Later on, the networks can change in arbitrary ways, but because this is a non-convex optimization, if you optimize the parameters of a neural network, we know that the initialization matters a lot and strongly affects the features that are ultimately learned. So that's it in terms of the methods that we have. And so here is again the experimental setup with a bit more detail. To test if these methods that I just presented allow to make networks compatible, we train one network on STL10, on the STL10 dataset, and one on the Cypher10 dataset. And then at test time, we just swap their classification heads. So we use the classification head of the Cypher10 network with the feature extractor and on the data of the STL10. So we recombine their components into a new network. And we directly test how well that new network performs without any fine-tuning. And we measure that with classification accuracy. And here for both networks, we use ResNet 56 as an architecture, and we split it into two components between stage 2 and 3, where everything below is the feature extractor and the rest is classification head. So here are the results. As upper bound, we have just training a model on Cypher10, testing it on Cypher10, and doing the same for STL10. So no recombination. And here, if we just train networks independently, and then we try to recombine them into new models and test that doesn't work at all. It performs at chance level as expected. However, all of our methods that try to encourage compatibility they indeed perform much better than random. Where just starting from the same weights already gives significantly better than random performance, and then the other methods perform reasonably well, and in particular their components do quite good. So this is not an obvious result at all, because now we have actually two network parts recombined into a new network, and that network is just directly tested. So for this, the features read to kind of feature dimension 0 needs to have a consistent meaning in both feature extractors, for example. Their magnitudes need to be reasonable so that they still work with another head and so on. So we were actually quite surprised that that works with 0 fine-tuning. And initially we wanted to do a little fine-tuning, but we figured out that you can actually do that right away with like what we call 0-shot recombination. So we can just recombine the components into a new network and test that, use it right away. I should also say that here the gap is actually mostly because of task mismatch, because we use a classification head from STL10 on Cypher10 and vice versa. If we train two networks on Cypher10 and have a compatibility force, then the gap to the upper bound closes much more and is, I think, 1% roughly. So far, I've talked about a joint setup where when we have an auxiliary task, like the one here shown in blue, we train both networks at the same time. So they both optimize the parameters to solve their tasks, but also the parameters to solve the auxiliary task. And so they both contribute to the parameters of this auxiliary task head. But we can also do something incremental. We can also do that incrementally, where we first train a first model that solves its own task, like classification on STL10, as well as rotation prediction, say. So in this process, it will produce the parameters of the auxiliary task head to solve the task. And then what we can do is we can freeze the auxiliary task head's parameter and then train the second model. So then we can do it in 2 stages. And because the second network still needs to solve rotation prediction, but cannot optimize the parameters of this auxiliary task head, what it needs to do is it needs to kind of produce features that work with this existing head. So that provides kind of a constraint on the features that this feature extractor produces. And because of this constraint, it will still be compatible. And here are the results for that. Joint training works better, but we can also do incremental training just by aligning or basically training a model against a frozen auxiliary task head, and that will still lead to compatible representations.
We don't see the results, Michael. Yeah,
what?
The plot just showed up, I guess. Yeah.
Okay,
maybe,
that's.
You can
for
repeat
me, it
what
showed.
you said, maybe. Yeah.
So okay, yeah. So it's maybe some sort of delay for me. It looked fine. Yeah, this is just the difference between joint and incremental training, where we show that we can also train incrementally, and we lose 4%, but it still works quite well. And this setting is quite interesting because we'll use it widely in our applications. So yeah, this is, I think, maybe a bit abstract. I mean, maybe now is a good time to ask questions, and then I'll talk about applications, and then we can again have some time for questions.
Yeah, I forgot to mention, but Michael said that he has multiple parts in the talk. So at the end of each part, he will answer the questions related to that part. If there are any questions about this part, go ahead.
Maybe I can ask a question. Michael, did you try to explore how the learned filters are compatible with each other?
Mm-hmm.
Like for example, how they differ in especially early layers and so on.
How they, sorry?
How the filters differ at different layers.
Well, we did two things. Maybe not exactly what you were asking, but we did two things. One, we looked at what layer do we like split into feature extractor and classification head. Like we varied that point and checked like where is it easier to make parts compatible or not. So that's one thing. And then the second thing that I had that is hidden here, I think you can see it now, is we looked at how much do the feature activations correlate when the feature extractors are presented with the same input.
Exactly what I tried to ask.
Okay, right. So yeah, we have results for that. Let me go here. So this is the so basically, if you train independent networks, then the features are not correlated at all, right? So even if the networks would learn the same things, they would be in arbitrary order. So dimension 0 would not have consistent meaning. So the correlation is almost 0. And then there's like previous methods that did kind of this post hoc analysis of checking whether networks learn the same thing. And one method just tries to find or finds an optimal permutation of the feature activations produced by one network to the feature activations produced by another, and then looks at under this optimal permutation, what's the correlation of the features produced by the two networks. And this is at like 0.34. So there we also already have kind of, they correlate reasonably well, even if you train the networks independently. So they do tend to somewhat learn similar features, but in arbitrary order. There's a whole line of work that looks at what is consistently learned and what is not. So often, like face detectors, you know, like detector of round objects of certain patterns, they're consistently learned, and some other are not. Or often, like a certain pattern is kind of recognized by more than one feature. So there's not a single feature that kind of detect. You know, a set of features together would detect that concept, not a single one. So that's for independently trained networks. And then when we optimize for compatibility, we can somewhat increase that correlation. And here, because we have a force that tries to align the feature space, we don't need that permutation. We basically directly take the output, which here leads to random correlation. With compatibility, it's much better than random and can get rather high. So this shows that it kind of helps align the feature space in a way. Does that answer your question?
Yeah, definitely. Thank you.
Okay, sure. Okay, then I'll maybe continue. So the first application we used is classifier transferability across architectures. So the idea here is that that when you have kind of incrementally add classes to your classifier, currently you have to retrain a full model, right? And this becomes a problem if you, let's say you have multiple models to solve the same task, but each one has a different architecture, which often happens if you kind of have a network that runs on a server, then you have like a network with more capacity and maybe this needs more compute time or compute power. And then on a mobile phone, you maybe have a model that classifies the same objects, but is much more lightweight. And currently, when then you increase the number of classes, you would have to retrain each of these models to then, so that they can classify all the classes. And our idea is that we can just make all the feature extractors compatible and then make that process simpler. So the approach we use is first we train all feature extractors with the same classification head so that they're compatible. And then when we extend the number of classes, and in this experiment, I should say, we start with 5 Cypher 10 classes, then we add the remaining 5 so that we go to 10 classes. And so if we go to the 10 classes, we would just fine-tune the classifier together with one backbone. Here we use the Resident 56 backbone, which we freeze, and then we have a classifier that can classify all 10 classes. And then because all the backbones, all the feature extractors are compatible, we can just transfer that classifier onto the other backbones, even though and to get a new model. So we get kind of the mobile model with a combination of feature extractor and classification head that was never seen during training, and then directly use that model. And here are the results for that, where as an upper bound, we have kind of the brute force thing that I introduced earlier, where we just retrain every time all the models. And the lower bound is just correctly classifying the initial 5 classes, but not the rest. And here we get quite close to the upper bound, which this shows that basically we can produce a classifier on one network and then produce it to the other ones. At minute, we lose some accuracy compared to the upper bound, but it works reasonably well. And again, here the gap is partially because we don't have perfect compatibility, but also partially because we kind of unified this classification head. So it's not the optimal classification head for all the feature extractors, just because we need to kind of select a single one. The second application that we tackled is transfer learning. In transfer learning, the goal is to perform well on a target task by reusing knowledge derived from some related source task. And the key question here is, what's the right source task to select? So often the problem is estimating how well will a source model then perform when it's transferred to the target data set. And the brute force approach, which was, for example, taken by Amir Samir and colleagues, is to just train a model on each source data set, then fine-tune it on the target data set and test how well it does, and do that for all the potential source data sets that you could select. But this is quite heavy computationally. Oh, and sorry, then yeah, once you did that, then you kind of know which source model works best, and you can just keep the best one, right? But just fine-tuning a source model on the target, in their case, took like 17 GPU hours, and they had a lot of source target model combinations. So in total, they spent 50,000 GPU hours to kind of find good transfer combinations. And instead, we kind of want that make that faster with compatibility. And the idea is that we train all source models against the same auxiliary task head that is frozen, and then all the target data sets as well, so that their model components will be compatible. And then at test time, we can just basically try the source feature extractors with the target classifier and test how well that does on the target data set. So this kind of gives us an estimate as to how good a certain source model is suited for the target task. And here, optionally, we can fine-tune a little bit. And again, we evaluate how well the source does on the target and keep the best combination. And so this is much faster, where the cost of adaptation decreases to less than 1 GPU hour, and that is mostly spent on evaluation on the target data set, target test set. So here are the results for that. What we do here again is, for example, we take a feature extractor that's trained on ImageNet together with the STL classification head, and we test how well that combination performs on STL10. And if we don't have any compatibility method, for example, by just training the models independently, we get chance performance when we don't do any fine-tuning. Fine-tuning is here on the x-axis, sorry, and accuracy on the x-axis. So if you just recombine these components with independent training, you get random performance. However, if you train them to be compatible, these parts, then you can directly test this new model combination, get an estimate of how well the source feature extractor, how suitable the source feature extractor is without any fine-tuning. And then, of course, you can fine-tune this new combination, and performance will improve for both cases. And eventually, they would converge to the same point. But for ours, you need much less fine-tuning. And this is kind of a pattern or a result we see on all the data sets we tested. We also tested on Cypher 10 and on Cypher 100. The third application we have is similar to transfer learning, except that it's unsupervised domain adaptation. So here, in contrast to transfer learning, we don't have labels for the target domain. So we have a labeled source domain and a non-labeled target domain. And what we do in this case is we first train a model on the labeled source dataset to solve the source task and an auxiliary task. Again, here, a self-supervised rotation prediction. Then we freeze the auxiliary task head and fine-tune the feature extractor on the target domain. And because this auxiliary task head predicts rotation, which is unsupervised, we can then do basically fine-tuning on the target domain without having the need for labels. And because we freeze this auxiliary task head, this kind of provides a constraint again on the features that can be produced by the feature extractor here, and prevents it from becoming incompatible with this classification head from the source model, so that we can then recombine them and test on the target dataset. And here results for that. Just using the source model directly on the target domain gives like 65% classification accuracy. Instead, we were doing much better, roughly 78%. And here, we also have another baseline where the batch norm parameters are optimized for the target domain, which performs also quite well, but not as well as our method. In comparison to state of the art, we're within 1% of the best performing model, and this model is much more complicated. It combines, it's really like tuned for domain adaptation, combines 7 loss functions, has a custom architecture, and uses domain discriminators. And it's actually jointly trained on both datasets, or domain, the source and the target domain, which is quite, it's computationally heavy. So in conclusion, we have shown that we can train networks to produce compatible features. And in fact, that is something that I didn't talk about, that's in the paper. We can do so without compromising the accuracy on the original tasks. So it's not a trade-off. You get basically more compatible features without doing better on the main task. Or sorry, without doing worse. We have shown that we can get compatible features through joint training, or also by making new components compatible with existing ones. And by showing benefits in free applications, I've shown that our idea of, or this concept of compatibility is widely applicable. That's it for this part. If you have questions.
Yes, can I ask a question?
Mm-hmm.
So I just want to understand the extra fine-tuning that you do with the target domain. You said
for
you
domain
freeze
adaptation.
Yes. So there is 2 heads. One is your rotation. What was it? Sorry.
Rotation prediction head. Yeah.
Yeah, the thing that you introduced. Okay, and there is the classification task, of course. So you freeze the classification task.
Yes, just ahead of the classification task. Yeah.
Okay,
the green
and
one
then
is not.
and then just using the unlabeled target examples, fine-tune with the rotation prediction task
as a training signal. Yeah. And this will update the feature extractor.
When testing for target data, you just use the newly trained network with the already freezed classification head, right?
Yes, correct. Yeah, we first produce it on the training on the source domain, and then we copy it over and test it with this updated feature extractor. Yes.
So you never update the classification head, even
No.
though you updated the rest of the network.
Yes. Well,
How
we
do
also
you
didn't update the auxiliary task head, right? So this is frozen as well. So we only update the feature extractor.
Yes. So numbers change. Your features like maybe move to another space, let's say, without like some kind of update to the freezed part, the classification head, how do you get these results?
Well, I mean, so this kind of provides a constraint, right? So that's one thing, and then we use a reasonably small learning rate. So it mostly updates. It does kind of fine adjustments to the target domain.
Like, do you introduce new regularization losses? Maybe some, like maybe don't diverge from the old features.
No, we just keep this head frozen, and that's it. And I think we do like 1,000 steps. So I think, yeah, I think, you know, well, two answers. One is we've seen that actually these networks can take quite some change and still be compatible. So they're quite robust to changing features.
That general, come on.
Yes, there will be a point where it breaks down. If like the source, like if the source domain is consumer photos and the target domain is medical, this would not work. As long as the changes are kind of small, then the changes to the network are also small, and then it's robust enough to.
Did you work with any text data?
No. And a second answer is that actually one thing that was key was recomputing the batch statistics of this new combination here. So we recombine the batch statistics, and because the batch statistics, not the learned scale and offset, right? Just the mean and variance, and this kind of normalizes the scale and offset.
Yeah, yes, I can see that. I can see this working with CNNs, maybe. Yes, that might be the like limit of it, though. Like maybe this wouldn't work with text or some other architecture. I'm not really sure.
Yeah, it depends how. I think it depends more how big the domain gap is between the source and target domain. And yeah, I think it's not quite clear, but I think you're right that there's a limit of, you know, like small changes the network can handle, but eventually it could become so big that it would break down. But like just to show you that, I briefly showed this correlation, right? And here the correlation is not very high. Is maybe we have like 0.38, 0.19. So the features of the the feature extractors, they have a correlation of 0.19, and that is still enough to get 70% classification accuracy on Cypher10 and STL10. So that is quite surprising,
this is
actually.
Really intriguing, yes.
So indeed, actually, we're surprised that yeah, these networks are quite robust, and as long as again, like batch statistics are recomputed. So if kind of the scale of the features and the offset changes a lot, then the results are worse. So we have in the supplementary, we have all kinds of versions without updating batch statistics, and then it works worse. It still works, but I think this is, well, either you update batch statistics or you use something else than batch norm. So use instant norm or group norm. But this normalization is kind of key.
Thank you for the answer. Great work.
Sure, thank you.
Can I also ask a question?
Sure.
So about the self-supervised learning task that you used, rotation prediction, is there anything like special about it? Did you try different types of tasks, or you know, do you think that maybe it would make sense to, based on the task that we're trying to solve, to maybe try some other type of self-supervised task? Yeah,
that's a great question. Definitely. I mean, the honest answer is that it's so simple, and we wanted to try more things. But so I think it has a good trade-off, rotation prediction. It's terribly simple to implement, and it works well. But there's better ones. There's all this like SimClear and all this like contrastive prediction methods. And I do think that the stronger the self-supervised task is, or strong is maybe the wrong word. I think it should have two properties. First, it should use all the features that are produced by the feature extractor, because if it only uses a subset, it only puts a constraint on the subset, right? It only regularizes that subset of features, and the other ones could change in arbitrary ways. That is kind of one thing. And then if the self-supervised task is as similar to the main task that you want to solve as possible, then that is also better, because it will kind of regularize the features more that are important for the main task as well. Or you could, and also it will not kind of produce conflicting gradients. In the extreme case, you know, if the self-supervised task is truly orthogonal to the main task, well, then you could kind of have this case where the main task gets worse by having this self-supervised task in addition. So it's really, yeah, I think, you know, there must be better ones, and this is something we unfortunately didn't get around to, but I think there's a huge potential. Maybe a word on orthogonal. We get even like slight improvement by adding rotation prediction, because it adds an additional training signal, and the two tasks are similar enough. But so in practice, it happens rarely that you kind of hurt the main task's performance by having an auxiliary self-supervised task, but of course there's no guarantee, right? So yeah, it's really quite an open research topic, I would say.
Okay, yeah, thank you.
Sure. Maybe another word is that, you know, in this case we care about compatibility, but there's also works that try to make performance on the self-supervised task better by, in addition, having some self-supervised task, right? Especially if you have like semi-supervised learning or functional learning, and there you have exactly the same questions. What is kind of a self-supervised task that is close to the supervised task and helps benefit it? Yeah. So let's talk about the second paper. I can see we'll be running out of time for the last part, but it's okay. So in this paper, it has the title "Continuous Adaptation for Interactive Object Segmentation by Learning from Corrections." And so this was done together with my previous intern, Theodora, as well as Jasper and Vito from our group. So the task in interactive object segmentation is to kind of outline or cut out an object of interest. And typically this is done with some computer vision model in the background that a user interacts with. So the user provides some input, the model makes a prediction, and then that iterates. And here, for example, you know, if you don't provide any signal, the output could be quite bad. And then the user maybe says, no, this is in fact background. And then the model would update its prediction. He would provide, again, information that this should be background. The model updates its prediction. And this iterates basically between a user giving like a correction signal and the model updating its prediction until the annotator or the user is happy. Previous works tackled this as follows. They basically provided the image and the user corrections encoded in some guidance map that could be a distance map or just like Gaussians placed where the user clicks. They provide this as an input to a network, and then the network would, given this information, make a prediction. And again, this iterates, as I said. So the user corrections here are input to the model. And the model parameters, so the mapping that takes the image and the corrections and produces a segmentation mask, the parameters of that model are optimized during training time and then frozen at test time. So the corrections are inputs to the model. And this works well because now imagine, so these parameters, they're updated on some training set, right? And then we use that model on some test set. And this works well if the training set and the test set have kind of similar distribution. Say you have a training data set where you produce segmentations on Pascal, or train the model to produce good segmentations on the Pascal training set. and then you test that on the Pascal test set. So that works well because they have the same types of images, the same object categories, and so on. But in practice, actually, this almost never happens. Often the training and test distribution are quite different. As an example, I was working at gifs.com, and we have this paper here on interactive video object segmentation in the wild, where we in fact did train a model on the Pascal VOC dataset and then used it on the website, where we allowed people to segment objects. And the type of images you see are just very diverse. You see like aerial data, you see comics, you see synthetic scenes. So now we were actually using a model that was trained to segment the 20 object categories in the Pascal dataset, and were used for just anything you can imagine. So that model is obviously ill-suited, right? And what happens then is that it produces worse and worse predictions as kind of the difference between the training and test distribution increase. In particular, when there's a domain change, so you train on consumer photos and you test on something like aerial or medical data, then such a model performs really quite poorly. So there's some other works that try to improve generalization in such a setup, which I mention here. There's two in interactive segmentation and one more generally that does out of distribution generalization. So here's our main idea. When a user clicks and says, oh, this pixel should be background, when it was in fact foreground, or the other way around, then each time a user does that, or an annotator, they in fact provide a training example. They provide a ground truth label for one pixel in the image. And the key idea here is that we can not just use that information as inputs to a model, but we can use them as very sparse training examples to update the model parameters at test time. So compute some gradient, do a gradient descent step. Produce new model parameters that work better for that image. We use that in two ways. The first one is that every time a user clicks, we update the model parameters. So we kind of overfit the model parameters, the appearance model or the mapping of that interactive segmentation model to a particular image, and then use that updated model to make new predict the segmentation mask. And this already makes much more plausible predictions, and it quickly learns the appearance of that image, and hence works quite a bit better, as we'll see. The second way that I think is more interesting, at least for me personally, is to use that on a sequence, that idea of adaptation on a sequence of images. So assume that if you want to annotate a data set, maybe you want to annotate an aerial data set, then all the images would kind of have similar appearance, or at least the modality would be the same. It would always be aerial images. And in this case, what you can do is you can, after you kind of segmented an image, and you're happy with it, you can then use all the corrections from that image to produce a new, to update the model, and then use that updated model when you start segmenting the next image. What that means is that your model, your mapping that maps from image and corrections to a segmentation mask will adapt to the sequence that you annotate. And hence it will be better and better over time. So here, similar to previous work, we kind of need an initial model, right? And we train this with simulated corrections that we train it on the Pascal dataset. So the input is the image and a set of generated corrections, and the output or the ground truth is the dense foreground background segmentation of the image. And we just use the standard cross entropy loss here, which is standard practice. And we have dense labels, right? We have dense supervision. But then rather than stopping there, we also adapt at test time, where we still use cross entropy, but just very sparsely. So we basically ignore all the pixels for which we don't have corrections, and we compute the cross-entropy loss only over the handful of pixels which were corrected to then update the model parameters. Because here this is very sparse information, we add regularizers that prevent forgetting, because, for example, these sparse corrections don't provide information about the spatial extent of an object. So there could be degenerate solutions if you don't take special care. And we do this in two ways. The first one is we also use the predicted mask as a ground truth with some low weight, so that basically the updates are kind of contained and are still producing, like, I think here what the model has learned is some objectness prior, and we kind of want to retain that objectness prior. And the second is we regularize parameter changes. So we basically have a penalty for changing important parameters, where the importance is estimated by a method called memory-aware synapses. So with our model, we can adapt to distribution shifts, new classes. So for example, since we train on the Pascal dataset, we have never seen donuts, but then if you use that model to segment donuts, the baseline, which is keeping the parameters frozen at test time, can perform quite poorly, and instead we do much better. And we also apply it to domain changes, as I mentioned initially. So so in terms of numbers, we measure the number of clicks, the number of corrections a user needs to make to reach a certain segmentation accuracy. And here the model is initially trained on the Pascal VOC dataset. And then we test it on video datasets where we use 8 to 30% less corrections. We use it by just segmenting images of a certain class. So we segment, like, let's say 100 images with umbrellas, and then the model will adapt to be good at segmenting umbrellas and hence perform much better over time. And here we need 12 to 44% less corrections. Then if we really change domains, so we start segmenting rooftops or aerial, or medical images, we get like a reduction of 66 to 77%. This will maybe be a bit more concrete when we look at this plot, where we look at the number of clicks that are required to reach a certain segmentation quality as the number of images that the model was used on. The baseline, which is just keeping the parameters frozen at test time, always needs roughly the same number of clicks, right? Because it's always the same model. And the same is true for when we adapt the parameters for each image individually, which uses the clicks more efficiently. So it performs better, but it doesn't improve over time. And a model that updates the parameters after each image and hence like kind of moves them to work well for the data that it's tested on, here aerial data, will need less and less clicks to produce good segmentation masks. And here I think you can see we have 4 clicks for the frozen model, still produces pretty poor results, and our method produces nice segmentations of roofs after just a few clicks. So in conclusion, by learning or using the corrections as training examples, we make more efficient use of them, and less corrections are needed for high quality masks. And actually our method, which adapts the model parameters, is most useful when the training and test distribution differs, because it kind of is able to bridge that gap. But as I mentioned initially, this is actually the most common case. You always have, or almost always have, distribution changes. And our method outperforms the frozen model on 8 datasets, where some of them I mentioned in this talk, but I think we tested two more. And because it's a scheme to update the model parameters, it's kind of agnostic to the model and backbone that you use. You can use it with anything, essentially. And in our work, we use DeepLabV3, but we're not restricted to that. Here are a few more results. on the top left, you see the baseline, which keeps the parameters frozen at test time. Here we have optimizing the parameters for each image. Here we have optimizing them over a sequence. And here's the combination of the two, where we both, after each image, produce new initial parameters. And then when we segment an image, we overfit the parameters to that image as well. So this works best because it kind of combines the advantages of the two, which is kind of having a good initial model and then really adapting the parameters to one specific object or image. Here's another example. And yeah, that's it. So please feel free to ask questions. I think we'll not start with the last part because we're already almost out of time. So I think it's better to just spend some time on questions.
Yeah, that's a good idea. Very cool work, Michael. Nice
Thanks.
Visualizations.
I have to thank Theodora for that. She did all this nice animations.
Nice. Maybe I can ask, like, it's very clear how Google can use the first part. Like you explained 3 different applications. What about this one? Are you like, is anyone at Mechanical Turk using these kind of things to make these miserable people's lives a bit better?
So we that's a loaded question. No, so there's a paper by Rodrigo Benson, also from our group, together with Stefan Popov and Vittorio Ferrari, where they used interactive segmentation to annotate 300 classes from the Open Images dataset, and they released, I think, maybe 500,000. I'm not sure about the number, but a large number of segmentation masks for these classes. Let me switch them because there is use to that because it's much faster than doing it by hand. So we're actively working and using kind of these tools to make annotation more efficient, because as a way to produce data sets that are then used for downstream tasks like throughout Google. So this one in particular we didn't deploy because it's kind of hard to deploy in practice because it requires adaptation. Like you need to run a neural network in the browser essentially to do it. Yeah, I think we're in general, we're interested. I should maybe also mention speed. So speed is fast enough to do interactively. I think it takes like half a second to update or even less. So that's kind of okay, but you need a heavy network, right? And so I think this particular network we're maybe not gonna use necessarily, but having models or vision models that, or just, vision models that adapt to the data that they see in a similar way to the losses I described here. So that's something that we're very interested in because it will just make the tools much more robust. Because indeed, like, then like somebody wants to, somebody comes wants suddenly medical images. And if you have an adaptive model, then you can just start annotating, segmenting these images right away. If you don't, then there's an engineering effort. You need to, because a tool like this, it works well if kind of the distributions are similar. If the distributions are different, then it's difficult. So what you would do if you don't have an adaptive method, you would first kind of with polygon tools annotate the first masks. Then you would update the model, learn a mapping that works well for that type of data, right? So you learn the initial model parameters, and then you could start and go and annotate. So this is quite the effort. If instead you have an adaptive method, you can just start right away. And especially with sequence adaptation, Maybe on the first 5, 10, 15 images, you would be a bit slow, but it would just adapt and eventually start to work very well. And this is kind of shown here in this curve, right? So this, I think, it's powerful because it's very robust. That's, yeah.
Yeah, it has a lot of potential for different domains, as you said, especially.
Yeah.
You should show it to doctors.
Yeah.
Any other questions? No. I guess we can conclude it then. Thank you very much, Michael. This was very interesting. Do you want to say anything lastly, or?
No, I think that's it. Yeah. Let me just go to the last slide. Yeah. Sure. Yeah. No, I think that's it. Thank you very much for having me. Maybe the only thing I want to highlight is that we have an interesting project called Localized Narratives, which I didn't get time to talk about, which is a large data set of speech annotations and mouse tracks. And it's a very powerful data source, and it's available online. So this is something that is interesting if you want to kind of do captioning or image generation. It's really a very rich set of annotations. But yeah, that's it.
Nice. Great. I'm gonna
Thanks.
stop recording.